Right. Well, welcome everyone to our second webinar in our exoplanet exploration series here this week and next week. Let me do some introductions for people who may not have been on last Monday's webinar. My name is Mary Dussault. I'm a project manager for the MicroObservatory robotic telescope system here at the Harvard-Smithsonian Center for Astrophysics. Also here as panelists who will be potentially contributing or able to answer your questions about the use of these tools are Martin Fowler, who's an amateur astronomer who's been doing great things with MicroObservatory and our exoplanet data from London. Martin, if you say hello, I think people will see you for a second.
Hi, everybody. Can you see me?
Great. And then following him, we have joining the webinar, Jim Kernahan, who's a high school physics and astronomy teacher at Milton Academy, a school south of Boston. He's used MicroObservatory for many years and always keeps us honest in terms of what's working and what's not. Jim, why don't you say hello?
Hello all, how are you? Happy to be here.
Great. And then our NASA colleague at Space Telescope Science Institute in Baltimore, part of our NASA Universe of Learning consortium, that's part of the group sponsoring this webinar series, is Emma Marcucci. She's a scientist who also works in outreach there from Space Telescope. Emma, why don't you say hello and people will see you for a moment.
All right, well, hello everyone. Happy to be here this afternoon or tonight or this morning, wherever you are.
Great. And then as I think you all have heard, Erica is also on the line and will be monitoring the chat box and the question box so that if I'm showing something and I don't see it, but she thinks it needs attention, she'll make sure we get your questions answered.
I can't say hi because I'm on your audio.
Ah, right. So there's Erica, and behind her is Roy Gould, who is the original developer of the ExoLab, and uh-oh, there we go, just turned my screen off, is the leader of our group, and he can answer lots of questions about the development of the ExoLab as well. All right, well, so Monday, we went over how to make photometry measurements, how to make brightness measurements in the ExoLab. Oh my, Adobe Flash is out of date. How does that happen? All right, I should have opened in another browser. Okay. Oh dear. I was just looking at this. How can it be out of date? Well, now you see the issue with Flash. Maybe I'll, yeah, maybe I'll just open a new window here. Let's try this. There we go. Right, and I seem to be not logged in, so let me log in for the workshop. All right, so now we'll go to the lab. And so you guys, teachers 3, 6, 9, 14, 15, 19, 23, and 31 were able to make measurements, and I thank you for that. So for us to now go see what they did, I'm in the image lab. I'm going to go back to show my list. I'm going to go find that TRES 3 from last Sunday into Monday. And I'm going to click on one of the images. It doesn't matter. Any image will tell the ExoLab, this is the planet I want to look at the data for. So now when I click on graph brightness, I will see the measurements I made of TRES 3. And you can see here, it's a little peculiar here. There's a kind of a little loop-de-loop, one way down here, one up here. It's not clear that I have done enough to see anything. But now I'm going to click on class graph. And there's all the data that you guys measured. And in fact, you can use these sliders on the bottom to kind of change the scale of your graph, get it into the middle here. We have these funny spots up here. So, so now this doesn't quite look exactly what the modeling lab looked like with that nice line that goes down. Remember, we talked about how the model of what a transit is supposed to look like is idealized, right? But of course, this is what real data looks like. And a few features of the ExoLab I want you to know about is that Kaylee's teacher 5. All right, let's see if I can find one of your points, Kaylee. So I have 4, 19. I'm afraid, Kaylee, I don't know whether you measured this. I'm not sure what happened with you. So we'll have to take that offline, and I will communicate with you maybe on the online community to see what happened to teacher 5. But we noticed that a few people here, teacher 9, 19, and 15, have relative brightnesses that are off the scale. In fact, you notice most of the relative brightnesses are kind of between 0.95 and 1. There's one of these here, teacher 9, has a measurement of 15, a relative brightness of 15, meaning the target star was 15 times brighter than the comparison stars. So I think something's gone wrong there, and it turns out ExoLab has some tools to analyze that, and that is that you can look at the raw components using this components feature here. If I click on that, we'll see the raw data, and you can see the target star are the green dots. The 2 comparison stars are red dots. And for TRES3, the comparison and target star all are about the same brightness, so they kind of overlap each other. But you notice there's this target star measurement way up here by teacher 9. Clearly, I think there was either not calibrated, you hadn't subtracted the dark potentially, or a wrong star measurement or a potential inadvertent click with your mouse so that you measured a bright star instead of the target star. So there's a number of things, but you can analyze when you see raw measurements that are kind of way off the mark from all the other measurements in the group. It can typically indicate that one of your students, if you were using the ExoLab, each dot would have your student name on it, and you'd be able to tell which student might have done an incorrect measurement.
So Mary, I think I figured out Kaylee's problem, and I think it'd be good to actually can you go to the show your list for a moment?
I can. So we'll go back to analyze images. I'll show my list. Did she use the TRES3 over here?
Yeah.
Kaylee, if you look up, you'll see those are demo images, and those don't get saved in any account. They're for people to use who aren't signed in, who want to know how this thing works. They don't have an account. So those, yeah, and I never even noticed that TRES3 is our demo. Yes. So those measurements were on a data set from 2013. You can see here, TRES3 130607. So there we have it. Got it. Okay. Well, there's a little troubleshooting there. Any image that you take yourself will be in the My Images list. So for most of you, as you signed in, you probably had nothing in the My Images list. They were all in the class images list. I, as the teacher, took all of them. So you can, this is a way you can assign certain images to certain students, and they'd be in their My Images list, but all the students would have access to all the images from that data set in the class images column. Okay. So let's go back to our graph here. Oops, my graph. There it is, class graph. Okay. So it's a little messy, but if somebody had to say when the transit might have been happening, maybe you might type in the chat box and say, when do you think that transit was happening? Does anybody have any suggestions in the chat box? Did it happen between 1:30 and 2:30 in Arizona? When would you say the start and end of it are? Between maybe 2 and 3:15. Yeah, okay, 2 and 3 a.m. Yeah, these dots are definitely, as a group, lower than the dots up higher. So the next portion of the ExoLab is called the Data Lab, and here's where you actually get to analyze this data set in light of the model of what a transit does. Let's see. So when you first open it up, you need to, under Other Stars, find the data set you're working on. And so notice that I had clicked on one of the demo images, so it's looking at that. But I want TRES 3 in my list from 2018, May 21st. So I'll click on that. And now here is that data. And as we go through the data lab, I'm not going to go through every page. The teacher guide on the Home for Teachers page really walks you through every page of this lab. But we just had our first impressions that we think we found something between 2 and 3 a.m. But there's a way to gather more evidence. We can show the astronomer's prediction of when a transit should have occurred. So here's that. So this is from the ephemeris, from the published ephemeris for this star. And so we look like we're in the right ballpark in terms of timing. We have the option to show others' data. So that also seems like we're in the right ballpark. But the power of this data lab is actually on page 5, which has to do with a modeling tool. This is a simple modeling tool based on physics, our idea that the star has a baseline brightness. There's a period of time during which the planet is passing over the star, so it's getting dimmer and dimmer and dimmer. There's a dip value, which is when the star is the planet is fully over the star, and then rising. So this is a simple model, but you can move the colored dots in this model to try and visually fit the data. And so this is basically a set of models that that you can really manually inspect the model space and figure out where the best fit is. Now, we have a little issue with this data set because of these points that some students did that are kind of way off the mark. So, so it's going to be hard to get a really good fit. but I think I'd go with that. And so you see over here, our estimated baseline is at 0.98. Our estimated dip level for this star is at 0.956. So we have a percentage dip of 0.03 over 0.98, so about 3%. You have about a 3% dip in the brightness of that star. So it's pretty amazing. A small telescope can actually detect a 3% dip. But we can actually use that value to calculate the actual ratio of the planet's size to the star size. And really, for that, basically, if you take, 0.03 times 0.03, no, have I got that right? No, wait.
I take the square root.
Take the square root of 0.03. Yeah, sorry, right. Take the square root of 0.03, and I don't happen to have a, thank you, Jim. I knew you would be there. So the square root of 0.03 is 0.17. So the ratio, this planet, according to our data, our results are that this planet is about 0.17 times the diameter or radius of its star. So it's pretty big. Jupiter's 10% of the radius of our sun. So if this TRES-3 is a sun-sized star, this is a wonkin' big Jupiter, really big hot gas Jupiter. And so we'll type that in there, 0.17, and this is very big. Now this is gonna, I as the teacher am putting some data in here, and I'm gonna click Save Work. Your students will save their work as well, and you have a way to actually inspect their work in the Manage page.
So this actually makes a good point, because someone just recently asked if the interface contains all the same information for the students as it does the teachers.
Yes, the teacher has a little more. So if I pull this down, because I'm the teacher, you'll see all you have when you're logged in is a place to log out. But I have a place to register students, and I registered teacher 1 through teacher 30. You could register student 1 through student 30, or however many students you have. I have a place to manage those students, and then I have a place to publish data. Only the teacher can publish the class data, and that's what I want to show you how to do in just a moment. But with regard to managing your students, when I click on that, manage, right, there's all my students, teachers 1 through 35. But I also have this, I have this little journal tab. Turns out, if I look at that, and I look at telescope, if I look at ExoLab, actually, I have a record of which teachers made which measurements. So I could see what my various students did. I can download it as an Excel spreadsheet if you want to take a look at that or whatever. You can see what requests, and it looks like none of you, actually, I guess I click on one of you, and you can see if you've made any requests. So you have a lot of tools for checking what your students are doing that your students don't have. I'm going to go back to the lab. I'm going to go find that TRES-3 again. TRES-3, there it is. I'm going to go to that page 5 Now, so I'm going to try and get back to where I was here with my fit. Every time you come to it, it'll be new. I think it was like 0.98 and 0.95. That's pretty close. Okay. The rest of the data lab helps you not only find the size, but use that model fit to calculate the period, even from one transit. If you assume that the star is like the sun, you can get a good estimate just from the duration of a single transit, what the period and therefore the distance from its star is. And in fact, if we go to that page here, actually, another way to get the most out of your data. On page 6, when you see, this is my model star. It's bigger than Jupiter, right? It's hot, looks like it's molten there. It's a hot Jupiter. If I hit Z on my keyboard, it stopped. Now you can see if I play around with the model, right? This is telling you that the depth of the transit that you measure is directly related by the square root of the percentage to the size of that planet. It's also telling you, if you've got a telescope like this with all this noisy data, could I make a measurement of an Earth-sized star? No, right? Not with the MicroObservatory telescopes. That's why we need telescopes in space to get rid of this noise, have more signal and less noise from all the things that cause this messiness, which include twinkling, right? Stars twinkle. The atmosphere, there's always a little bit of difference in each measurement you make. During the night of the observation, the star may have set, so there's more and more atmosphere, and so that's more and more noisiness. Could be the moon was out, and that causes noisiness. So all those things are what make this data a little floppy. Kaylee, yes. How to find the period from the transit duration. So this is on page 7. Oh, nope. There's yet another thing you can tell. You'll remember from our model, right, that in order to see a transit, you pretty much have to have a 90-degree orbit, right? 90 degrees to the axis of the star. If you do that, there'll be a period of time where you have a flat bottom to your transit. But if you have a grazing orbit, like this one on the right, your light curve will be more triangular, right? Because there's not very much time compared to the time it's egressing and ingressing, where it's fully in front of the star. So as you look at TRES 3, would you say its orbit is more likely to be edge on or more likely to be tilted? I'm looking in the chat box to see if anyone has any hypotheses. Yeah, okay, so Stephen thinks tilted. And we'll look at the NASA Exoplanet Archive at the professionals' results for TRES 3. But remember, their results are just results too. Roy always reminds me of this, that it's not that the professionals' results are better than yours. Your results are your results. You had an instrument that might have not had as high precision. Maybe some measurement, you haven't gotten as good at measuring things yet. But your results are your results. There are no answers in nature. There's only the results of your experiment. All right, so tilted, we think. And here is, page 9, I think, is actually where we're talking about, oh, page 8 and 9 are where we talk about the period, Kaylee. So just from Newton's laws and Kepler's laws, we know if something's closer in, it's going to go faster. And if it's farther out from its star, it's going to go slower. If we compare, this is a really nice little tool. If somebody were looking from TRES 3 back at, and we happen to be edge on to them, the solar system, they would, if they had a Kepler telescope, they might see an Earth dip that would take about 12 or 13 hours. If they saw a Mercury transit, it would take about 7 hours. Our transit, we said, was about an hour and a half. So it's kind of right in here. And the duration of the orbit, of course, is related to the period, right, of the whole thing, because it's part of that whole orbit. This graphs out that relationship. In the teacher guide, there's another way to actually calculate it mathematically, but I forget what these kinds of graphs are called. Something graph, no, but anyway, you can just read a nomograph. Yeah, you can read off the duration that you observe, which was about an hour and a half, and see that it's probably 2 million miles from its star. And if we think of the Earth being 93, let's round up to 100 million miles. It's about 0.02 times an Earth radius. Remember that, because we'll look that up in the NASA database as well. Okay. So now we've gotten all we can. We've made some conclusions. Now we're ready to publish our data for the rest of the ExoLab community. To do that, remember I said only the teacher can do that. And you do it by having on page 5, having set the baseline and dip level, type something in and hit save. The teacher has to do that in order to be able to publish. So now I've done that. We're going to go to the publish page. Publish. And it asks me, what star do I want to publish? Oh, before I want to prove to you that we're publishing now rather than do it. So where is it that this is going to be published? It's going to be published in the lab on the community page. Okay. And this is the community page. We have Jim's school here. So if I click on Jim's school, you can see they've published quite a few stars. Let's look at your HAP P20. Ooh, very nice, Jim. Here's your HAP P3. So that Jim's data is dark, and then the data from other groups. Actually, apparently, Jim, you've got 2 data sets in here, one with a capital M and one with a little m. So this is where your data gets published. Let's go back to our publish page. The star I want to publish is, oh, Kaylee, great question. Would you want to remove outliers? Well, our tool does not allow you to remove data. You can go back and remeasure them. So especially, you know, that one with the relative brightness of 15, it might be you want to go back and remeasure that and click calculate and record, and it'll put it back hopefully closer in the zone. But of course, you don't want to remove data that may be noisy for any number of reasons. So we kind of don't like you to be able to just throw out outliers because they're outliers. if you could inspect the image and see that there's something grossly wrong with the image, so you have an a priori reason that you would not want to use that data point, you might do that, except that our tool doesn't allow it. So, okay, so the TRES 3 is the one we want to publish. So there's some instructions here that are telling you to go to page 5, make the data fit, be sure to save your work. And I have, because you see that planet size of 0.17 is in there, and my baseline and dip of 0.98 and 0.956 are in there. It says my status is pending, and the publish results button is ready to click. If I hadn't gone to Data Lab page 5, there would not be a button here, because it wants the teacher to say, this is what we think this transit is, right? So I've done that with my class here, I'm going to publish the results. Our class data has been submitted. Let's go back to the community page. And we'll go here. And let's see, we can go by star or by, we are this MAST workshop. Let's see. Oh, there's our TRES 3. Let's see what we did. So there's our TRES 3 in dark, along with lots of other schools that have also done TRES 3. So we have Clark College's TRES 3. And so you can see each of these data sets. The Merritt School had a very nice TRES 3 transit. There's ours. There's Clark College. Very messy, right? But even with all those messy data sets, when you look at all of them, right, there's definitely, I'd say, about an hour and maybe 15 minutes that you would call the duration of, this is many different nights all folded on each other against the predicted transit. Okay, that is publishing in ExoLab. Now I'm going to go to the DIY tool and talk about publishing from there, and also talk about hosting a group. But before I go that way, I want to stop and see if there's any questions about ExoLab. Okay, all right, we'll move on to DIY. Okay, so I have my own account here. Okay. All right. So let's see. I'm going to go to, I think it's still loading here. We're having a little bit of time crunch communicating with our database. There we are. Okay. So if I go to my planet search, you see that I've collected a bunch of data over the last few days. And the, now I can't remember from Monday. Did we go through the, we did go through the measuring tool, the brightness tool. Yep, okay. So I actually have created some groups in DIY as well. Now, DIY allows you to create your own account immediately, but I happen to have, we've created some group participant accounts. So if any of you are watching this and you want to try any of this, if you log out and log in as Planet Hunter 1 through 30 at DIY.com, that would be this is our demo group account. If you, I'll do Planet Hunter, I don't know, 23 at DIY.com. And the password here is exoplanet, with the O being a 0. And this only gets said, you have to listen to the whole webinar in order to hear that password. It's not written down anywhere. So,
Lowercase e, right?
all lowercase. So I'm going to log in. And you see here, it's telling me, Planet Hunter 23, that I have 4 new groups. Well, if I go to those, Mary D, that's me, invited me, and invited all the Planet Hunters, in fact, to a bunch of stars. So if any of you want to try these Planet Hunter accounts, try the same thing. What you would have to do is join. So Planet Hunter 23, if I join Trez3, then I will now have in my planet search the Trez3 data set. And if I click down, there's all those Trez3 images. And I can click on one. I'm as Planet Hunter, a group of 30 that's working together. And I remember that I have to calibrate, measure star, the target star, and remember I happen to have done Trez3 a lot of times, so I happen to know, but you can pop up your Finder chart if you need it. But I'm gonna do star measurement 1, comparison, comparison 2, dark part of the sky 1, dark part of the sky 2, calculate and record. And again, this is communicating slowly with the, there it is. Okay, so there's my measurement. I go to graph brightness. Let's see about my groups graph. So there's my Planet Hunter 23. If I click on my group, well, my group so far, since I haven't told you guys about this, is only Mary D. So I only made four other points. Any of you, if you want to try these Planet Hunter accounts to do data again, you can do that. But let me show you how to host a group. If you're an informal educator, or you don't have time for the full ExoLab, or you have just a group of friends and you want to do this on your own, here's how you host a group so you can all work on the same transit. You go to My Planet Search. You go to host a group, and you go to create a group. And the way you create a group is by selecting the star that you want your group to work on together. And when I click on the pull down list, you have available to you all the stars from the current month. The one thing that DIY allows you to do, which ExoLab does not, is that it will reach back into data sets that MicroObservatory took during the past month and pull them into your account. ExoLab is day to day. You have to request the images to get them that night and have them in your account. So if I, and of course I'm Planet Hunter 23 right now, so I've never hosted a group. So if I choose, I don't know, Cotter 1 from a couple nights ago, I don't have any friends. I should definitely log out and log in as me. So anyway, DIY has these social media features. It allows you to make friends, to include friends in your groups that you know you're going to want to invite over and over. So you can have your students all make accounts. Then if you know their username, you just type those in and you can add them. So if I wanted to add Planet Hunter and I want to add Mary D. Okay, so those are now my group, and now those people are going to have a little flag telling them that I've invited them. So that's how you do group, allowing a group of people to all work on the same graph. But if you just want to work on your own graph and publish it, you can do that as well. And so now I want to talk about publishing DIY data, and then we're going to show some, we're going to have Martin talk a little bit about what he's been doing with DIY data. All right. So I think I have some data here that I can publish.
None.
None. Oh, I'm in Planet 123. Thank you. Whoops. Let's go back to Mary D. Okay. So there we go. Go to my, it's taking a while to communicate with the database to grab my account. I know it will do this. There we go. Okay. So now, yes, there's all my data. Okay. Here's WASP 39. I think I took a bunch of measurements of this. Let's check. Again, I'll graph brightness here. No, I did not do this graph. WASP 39. I know I have a WASP 39. Let's find it. Past. Oh, how about this one? There it is. Okay. So I only did a few points. Really, I should do more before I publish this, but I'm willing to take a chance. One way I can see if my data makes sense is if I go to interpret and share results. So I'm going to go to that. And I'm going to select my star WASP 39. Where is it? Oh. Why is it not loading? Let me go back. There's my image. There's my data. Graph brightness. Interpret and share. Ah. Oh no.
Is there another one you can do?
Let me try another one. Yeah, let's see. Oh, okay. Well, there's one. So, and in fact, it looks like I already did publish this, but because I wrote, this definitely looks like I detected the transiting planet. In fact, here's a reference graph of other people's measurements. Here's the predicted transit. Does seem as if I've captured that. So when I click on share my results, all right, it's now shared with the public in the community results, and you can reach that from both these. Essentially, again, you can select by star or person. Here's my data sets that I've shared, and I think we just did TRES2. Yes. And there's my TRES2 data shared with everyone. Here's other users' points. The predicted transit. Now, this is interesting because to me, I don't know about to you guys, to me, this looks like all the data of all the users who've published, like the transit is actually, I don't know, 10 minutes earlier than it's showing is the predicted transit. And if we have time, we might be able to show that is one of the things that your data on MicroObservatory can do. It can be checked against the ephemeris that we're using and that other scientists are using to see if that's the right ephemeris to be using. Basically, the software bases its predicted transit on a transit that happened a year ago, could be 2 years ago, could be 10 years ago. And it propagates the period forward for 10 years and says, okay, on that date, it should happen at this time. But if the period is wrong at the 5th or 6th decimal place, that period over that prediction over years can shift a little bit. And so your data can help discover and pin down the best period for each exoplanet. And
also depend on where the Earth is in its orbit.
Yes. Roy is pointing out another, if an individual transit is slightly off, one thing we do not correct for in our ExoLab and DIY, but professional astronomers typically do correct for, is where the Earth is in its orbit. So if the target star is on the same side of the sun as the Earth is 8 light minutes closer, well, it could even be 16 light minutes closer to that star than 6 months later. So that can also cause a shift. All right. So that's publishing, getting the in DIY. I actually think I'd like Martin, if you could come on and talk a little bit about one of the things that you can do with DIY data. If I go back to my brightness tool here, is if I look at my data, you can see that I have this option to export that data right here. So if I click on export data, a little text file with my measurements, my relative brightness measurements, and the time and the image gets created. And Martin has helped us figure out how we're going to use downloaded data to do some pretty nifty things. So Martin, I wonder if you could share your screen and show us what you've been doing.
Okay. Oh, stop it. Yeah. Do you want to continue? Yep.
Oh yeah, let me stop my share.
All right. Sorry. Nope.
And while Martin's getting set up, if people have questions.
Hi, can everybody see my screen? Good?
Yeah.
Yes.
Hi. By way of introduction, I've been working with using the MicroObservatory for about 7 years now. Initially looking at supernovae and following up the changes in light over time following the explosion of the star. But for the past 18 months or so, I've been concentrating on the exoplanets. What I do is I work outside of the DIY tool. Conveniently, the actual image files that are collected are available to download. So I will download a set of 50, 60 image files for the transit, and the example I'm going to use is TRES-3 to start with. I've over the past 18 months or so, I've built up a pipeline where I can take those images and automatically produce a graph of brightness of the stars. Sometimes it works, sometimes it doesn't work. The package I use is called MuniWin. It's a bit temperamental at times. But what I can do, and I can give you an example on this screen here. This is the Exoplanet Transit Database, which is hosted by the Czech Republic's Astronomical Society. And it allows you to actually upload your data and fit it to the model of a transit actually in the system. And here's the data that I produce from the exact data that you've been looking at, the TRES-3. It's not particularly brilliant. There is a hint of a dip, and this is actually when the predicted dip is. So I load the file up, I specify which planet I'm looking at, TRES-3, and lo and behold, actually, the model behind it can actually produce a transit. It's not very good. I find that sometimes if there's smearing of the stars, the actual Muni wind doesn't actually pick up the positions of the stars, and the photometry goes a bit awry. But what I can do is produce this type of result. I won't say anything more about TRES-3 because what coincidentally, well, not more than coincidentally, what was collected on the same date, on the 21st of May, was data for, oops, wrong one, another star called WASP-43. This is the curve that came out from the data. You'll see there's a bit of strong trend that goes upwards. When I actually run it through the model here, we can actually take out the trend. There are parameters you can use, either a linear trend removal or a polynomial.
And let me just interrupt for a second, Martin. That trend is because if you were in the ExoLab or DIY and you looked at the altitude, as we were observing WASP-43, it was getting lower and lower and lower in the sky and looking through lots of atmosphere.
Yep. And that's one of the things that you can actually pull out, just like you can do on the ExoLab with MuniWin. You can pull out it's called the air mass, the thickness of the atmosphere that you're actually looking through. So this is quite good because there is, I think people probably agree, there is a reasonable transit apparent here. There are some outliers, and we've had the discussion as whether do you actually include them, can you delete them. For some of them where it's pretty obvious that they are outliers, I tend to remove them, especially when you look at the image and find it smeared and actually the photometry has not worked very well. One of the benefits of the ExoLab, of course, is that the human eye is a lot better than the computer at actually fitting the little circle around the star to measure the brightness. The downside is that to do it with ExoLab will probably take you a good hour to work through a whole set of data. With MuniWin, you can probably do it in about 30 seconds. So there's a trade-off between time and quality. So the output from the transit, we can see here, it gives you an indication of the Julian date of mid-transit. This is, it doesn't work on normal year, month, day. We actually work here with Julian dates, which is one of the standard date formats that's used by astronomers. But we can get an idea of how long it's lasting for, the depth of the transit. One of the really good things is that with the ETD, and I hope once you guys at CFA have got things going with the ExoLab archive, you can actually upload your data to there, just like you can do with DIY an ExoLab. And the key thing that can actually come out of this is that you can actually get a series of plots. The first here, so these are all the data, 79 records that have been captured by mainly amateur astronomers for WASP-43. What you have is the epoch. So this is the increasing number of orbits of the planet around the star. And then a value that's called O-C, which is observed minus calculated. So the observed is my date, that I observe the date of the transit. The calculated comes, as Mary said, from the ephemeris, and here it is how you calculate it. And you can get an indication of whether, as Mary said, that if the period's correct, because if the period isn't quite correct, you'll find that these start to diverge. And if we have time, I can show you for ExoLab a different planet. But this is a really good plot for showing how good your how good your photometry is of the planet transiting the star, but two, also for learning a little bit about what the actual period is, because here you're going over the 8 years worth of data, so you can get a good indication. You also look at what the duration of the transit is, so you can do transit changes in the duration sometimes. I should go back to, of course, with the transit time, if you've got another planet that you can't actually see, you get things called transit time variations, and that can start affecting the actual observed compared with the calculated time of the transit. And then another example, here's the depth. But I think what you can see is that from the ExoLab, from little Cecilia with her 6-inch aperture, she's getting quite a good agreement with other astronomers who are tending to use far larger telescopes than good old Cecilia. Shall I show the X01, Mary? Can't hear you. I can't hear you.
Sorry about that. Recently, Martin was observing what we hope to be a new target in ExoLab and DIY. It's called X01. And usually we have him try out our new targets before we make them public. And he found something really interesting because, actually, could you go back to the page you were just on?
Yep.
This is all the data for X01 on the NASA Exoplanet Archive. And this is what I wanted to tell you guys about. We're not going to have time today. I will definitely get to it at our next webinar. But you can look up any of the planets you observe to see what the published professional results are for that planet. So you can search TRES-3, which we just did, and it'll give you all that information. And we'll take a look at that later. But for X01, it's highlighting, as you see here on Martin's screen, this recent value for the period of 3.914153 days. And so Martin used that value to plot his data of X01 from MicroObservatory on that ETD or check site. So why don't you show us that, Martin?
Yeah, I've just got to quickly go through here. So this is the light curve I got. It loses a little bit because it's quite a long transit, but if I go to here, and what I'll actually put the no, hang on, let's put this, let's paste as plain text plot. Okay. So this is using the value here, which is highlighted in orange to show this is the default parameter. I don't know whether this means it's the best parameter. I haven't really got to fully understand what default means, but you'll see that actually, if it was correct, in inverted commas, you'd expect all of these data points to be aligned here. What you can do with, as I've shown, you can actually change this value. Let's try a different one. Let's try one that's probably, I don't remember which one it is now. Let's try this one. Put that in. So this is a shorter period now, 501, not user data, which is that. And you'll see, actually, it's getting a lot better. It's probably a little bit too long, so I think I can make that probably 2 and replot. I should have written down the figure that I actually used. But the whole thing is that you can refine and you use more sophisticated, use linear regression and other things to actually refine what a period could be.
And this ability, because we observe new planets every night, we're actually hoping to be observing hot Jupiter candidates and slightly smaller observed by the TESS satellite, the new NASA mission, to help pin down the period. That satellite is going to be making lots of discoveries where it predicts the next thing should happen on this date, the next thing should happen on this date, and there aren't enough people observing for all those candidates to check to see if the next transit really does happen when the satellite predicts. And so we hope to be one of the places that will be checking on some of those candidates. And you, as an ExoLab or DIY participant, will be able to help NASA figure out and pin down the periods of these newly discovered exoplanets. Next week, Rob Zellam's going to tell us more about that when he talks about TESS, and that's Tuesday after a long weekend here in the US. Martin, I want to really thank you for doing your demonstration here. I think you give us a peek of what can be done and help us see all the exciting things that we can do with ExoLab and DIY in the future.
Yep.
There have been some questions coming in. I know, Jim, you've been trying to handle them all, and Erica, are there any things I need to get to before we sign off for this week?
Oh, Jim, you're muted.
Jim.
Would it be possible to actually download some of the images? Someone had asked.
Yes, so let me share a screen here again. Okay, and so if I go back to my planet search and I see these WASP-39 images, here next to every image, there's an MO link. And if you go to that MO link, there's the image, and here's the FITS file. And so you can right click, save link as on your own hard drive. Then you go back to the next one, click on it, save link. Unfortunately, you have to do these one by one.
Mary, can you actually go back to that? I think there were a couple questions about those X's.
Yes. If there's an X, it means that that was a scheduled image, but for some reason it didn't get sent back to the server that provides it to this account. So it could be it didn't get taken. It could be that it didn't get taken at the time it was predicted, and there's a little bit of a your account is looking for an image that didn't get taken at that time, so it goes on to the next one. So the X's are images that didn't get taken. The green check marks did get taken.
And could you expand upon that, because Juliana was curious about when if there's any reasons her images wouldn't come back to her. So those are kind of the unique one image at a time, but not a whole data set, correct? If she requests a data set. I think there was concern about that.
All right. In DIY, or ExoLab for that matter, if I go to DIY, And I choose here for tonight, TRES 2. If you want all the images, you need to click on the All Hours button. If you only choose 1 a.m., 1:36 a.m. and take that image, no, it's not. Oh, it's communicating with the database. It's only going to take that one image. So you really want to click on All Hours, take that image, and then it's going to take the whole data set and put it in your account. Although I think there's a lag with the database at the moment. I'm going to have to check with our developer on that. Oh, there it is. Okay, so 71 images requested. So I just requested all 71 images that are scheduled for tonight of TRES 2. And to answer Juliana, anyone who uses DIY today is going to get the same 71 images in their account. But of course, every person is different, their level of precision, their experience doing the measurement. So in fact, different people will get slightly different looking light curves. And different people can publish them of the same data set, and that's fine. But one of the ways we can allow thousands of people to have the experience of detecting exoplanets is by asking for a new fresh data every night, but everyone who asks for it gets the same data set. Great. So we will send out the links to the recording of this webinar so that everybody has that. And our next webinar again is on Tuesday. It's around the frontiers of exoplanet science. Rob Zellum, a scientist at NASA JPL and who is working on test mission science, is going to talk to us about some of the frontier exoplanet research going on. So I want to thank you all for joining us, and